That's the engineer in us all, isn't it? Okay, well, we're all set for the next talk. So our next speaker is Dr. Gerald Gilbert. Jerry is from the MITRE Corporation and heads their Quantum Information Science group. He received his PhD from the University of Texas. He has a very distinguished career working with Steven Weinberg from Texas, and also with Stephen Hawking and some of his students. He will describe some challenges in quantum information science. Thanks, Jerry.
Thank you very much. Do I need to attach anything to myself? Or?
I don't think so.
Okay.
Are we okay?
All right. So it's a pleasure to be here. Thank you, Marco, for inviting me. It's nice to see some old friends. That by itself makes this trip worth it. You're supposed to start with a small joke. You mentioned quantum jokes earlier. They're usually not funny. But my office is, I'm at Princeton University, and that's, of course, in New Jersey. So the joke that usually isn't so funny is that, unlike saying I'm from New Jersey and I have an offer you can't refuse, and I say I'm from New Jersey and I have a presentation you can't understand. So we'll see how it goes. Is this the right thing to push the button? Okay. Why is it working? So you mentioned I'm a theorist, not an experimentalist. So.
You have to use the mic. So okay, so that, yeah.
Okay,
there
thank
you go.
So I'm going to just give an overview of the entire field to try to fill in some gaps. You're moving your hands. Is there some reason for that?
You have to speak into mic.
Okay.
Because not everybody can hear.
Gotcha. So I'm going to give an overview of the field that will hopefully fill in perhaps a few gaps, and it's always a good idea in any event to repeat complicated ideas. The overall field of quantum information science, or QIS, is built up out of three parts that are somewhat interdependent. These three parts are quantum computing, sensing, and communications. The three parts are not the same, but they share each of them two aspects in common, besides the obvious linguistic fact that the word quantum is in each of their names. They each solve a problem set that are otherwise either physically impossible to solve or effectively, practically speaking, impossible to solve. That's one of the two things that they share in common. And the other is that they achieve this by us in our design of equipment that does this, directly exploiting one or more features of the physics of quantum mechanics in the design of the hardware and in the design of the algorithms. In these three fields, I could go on at great length about interesting, challenging problems that we already know solutions for, that are otherwise not possible to solve in the classical context. But I'm just going to give a couple of examples. These are probably well known to everybody here. But in the case of quantum computing, we know that there are problems of a mathematical complexity such that we cannot solve them using classical techniques. The most famous so-called killer app that everybody must be aware of, I'm sure, is the Shor algorithm that is used to break cryptographic codes. I want to stress, just as an aside, that the Shor algorithm is not known. It's not. We don't have a proof that there is no classical method of doing what the quantum computer implementing Shor's algorithm does. There are quantum algorithms that can solve problems that no classical machine can solve, for which we do have such a proof. But this famous killer app, the Shor algorithm, isn't thus far like that. We don't yet have a proof that it's not possible, although it's probably not possible. Quantum sensing is putting on the best pair of glasses that you can put on. So I need to put on reading glasses to read. Quantum sensing achieves the best possible image resolution that is allowed by the laws of nature as we currently understand them. And quantum communications is a bundle of protocols. The one that's been mentioned most often thus far today is quantum key distribution or quantum cryptography. These two phrases are synonyms. The proper name, given what is actually done, is quantum key distribution, but it's too late. The wrong name, quantum cryptography, has taken hold and is It's not going to untake. So those are two synonyms that mean the same thing. With proper explanation as to what it is that you mean, it provides unconditionally secret method of communicating. I'm going to go into that in a little more detail. It was also stressed in the last talk. But I want to talk about the unifying feature that relates all of this, which is the generalization of bit to quantum bit. And what underlies that is the connection between physics, different parts of physics, and information theory. There's a syllogism here which seems almost like it's contentless, but it's very important, and it's not contentless. Information is necessarily encoded in the state of some physical system. I mean, if we want to communicate with each other or do anything with each other, we have to have a physical object at hand to do it. We can't just stare at each other. So there has to be a physical thing. And the behavior of physical systems, naturally governed by physical laws, determines what's possible. But the underlying basis of those physical laws today in the year 2018 is quantum mechanics. And we don't know of anything, we don't understand anything, we humans don't understand anything better than quantum mechanics. You can't think of anything. The history of Bolivia in the 17th century, the price of eggs in Kazakhstan, there's nothing that we understand better than quantum mechanics. There's no experimental deviation from its predictions that have thus far been verified. So therefore, I, as a physicist, can say I believe it. It sounds like a religious statement, but I believe quantum mechanics is correct. And so that actually describes what physical objects do. And if we impress onto the physical object the information, that tells us what information can do. So you've seen this chart before, but the thing on the left is a bit. It's, in this case, a capacitor. Well, my hand is a bit. If I hold it like this, it's a 0, and if I hold it like that, it's a 1. Any physical thing that I can flip between two conditions is a good candidate for a bit. There's nothing sacred about the number 2. The founding fathers of information science could have chosen base 17, and they would have had they been sadists. But there's Satanist too. But base 2 is as good as any other in terms of theory, and in terms of ease of thinking, it's the best one. So we are stuck with base 2, but it's a good thing to be stuck with. So anything that can be 2 valued is a good candidate for a bit, a classical bit. And that's all there is, and there ain't no more. A cup this way or that way is a bit. I don't really have to think too much. Well, if I'm Claude Shannon in the year 1942, I don't think too much about whether turning the cup upside down to make it a 0 or a 1 does anything special, because it doesn't. It's just a cup. Or it's a hole or a not hole in a punch card, or a tube that's turned on or off. I don't care about the physics of this. So here's my bit. I have charge or I don't have charge on my capacitor. But you've seen this sphere before. It's named after Felix Bloch, who was one of the great physicists of the 20th century. And you don't need to worry too much about the details of the mathematical appendages hanging off of this sphere. But it's a mathematical representation of a physical object that is what is called spin 1/2. But that, as Marco pointed out earlier, that is intrinsically connected to the theory of relativity, and that would take too much time to go into. But this sphere and where an arrow points on it tells us what are part of the state of a spin 1/2 physical system. And I can have it, and it's a vector, the characteristic spin that I'm talking about, and it points somewhere. I can have it point up. I can call that direction up if I want, and I can identify that as a 0. And I can have it point down, if this thing works, and I can call that a 1. But I can have it point here, and this is the really important quantum information departure from classical information. It's not just the tilt from the pole that tells you that you have some kind, in some suitable sense, of understanding this, an admixture of 0 and 1. It's also where it is in this angle as well, going around the vertical axis. That phase is not describable in a classical mechanical bit. It's not part of the classical mechanical bit. And this thing can point anywhere. And we now have the technological capability to swing that arm around anywhere we want. That's something we couldn't do 70 years ago, but we can actually take a physical system and make that arrow point somewhere. So there's a kind of, in a suitable sense, a continuous infinity of possible values that this bit can store. When we measure it, it always collapses into one or the other of 2 possible outcomes. But before we do that measurement, it's like this. I'm going to have to condense a lot. About a year ago, if you look closely, it would look like it's less than a year because the date that's on this paper on the right is just from a few weeks ago. But this is the third edition of this paper. John Preskill, my former colleague from when I was at Caltech, came up with a brilliant name, NISC, Noisy Intermediate Scale Quantum Technology. What he was trying to do in describing this was to capture where we are in the development of this field. The key to making any kind of quantum technology is to have a clean, error-corrected, fault-tolerant collection of quantum bits. And I'm going to talk about what error correction and fault tolerance mean in a moment. But we're not there yet for any reasonably large number of these things. But we're very close to being in a regime of actual building where we can have of order around 100 quantum bits. And they may or may not be perfectly error-corrected. So that's why he calls this regime noisy intermediate scale. The thing that is important for us to understand is that when we reach this value, like for example Google. Google has publicly announced they have a 72 quantum bit device. You can show theoretically that there are mathematical problems that are already impossible to solve with that number of qubits with any classical computer. So we're embarking now on a new era, we're in it now, of being able to actually develop hardware to solve problems that we don't know where it will take us. But this is what John stressed in his paper from almost a year ago. What I want to stress is not so much the quantum computing aspect of this, but the quantum sensing and quantum communications aspects. As it turns out, and there's no guarantee that this is going to be true for all of them, but most of the existing known quantum communications protocols and many of the existing quantum sensing protocols are different from the known interesting quantum computing protocols. The Shor algorithm that I mentioned earlier, in order to solve a meaningful code, to break a code, the machine, I'm not going to be able to go into all the reasons why, will have to have millions of physical quantum bits, most likely, based on our current understanding of error correction, in order to solve a national security type code. To do quantum cryptography, quantum key distribution, there are various protocols that have been invented. But if you use the simplest one, and the simplest one is as good as any of them, you only need to control at any one time, a unit of time in this discussion I'll call a bit cell period, 1 qubit. We can do that. And to do quantum sensing and get meaningful results that are better than the best possible classical results, you can already get that if you can control around 10 qubits at a time, as opposed to the millions that you need for quantum computing to give a real advantage. So we are already in the NISC era and have been for the last few years for sensing and communications. And this graph, this is a notional graph. I don't want you to look at the numbers that's why I made these bubbles intentionally kind of fuzzy. This is approximately correct. The 2 dotted lines there encompass sort of where we are internationally and how many qubits we can make in a laboratory. And there are various ways of parameterizing where we are in the scaling of quantum technology. I've chosen one way, and any one way that you pick, if it only has 2 axes, is insufficient. But here I have the number of qubits you can control, and then what I mean by control includes making them error-corrected, and the number of qubits you can make bang into each other in the vertical axis. These are logarithmic axes. And we're around, like I said, Google has about 72, Microsoft has what, about 50? That's approximate regime that we are. Many of you will know that there is a Canadian company called D-Wave that has, it claims that they have and does have 2,000 qubits on their chip. And they're using superconducting qubits. I'm going to show in a moment that there are different types or flavors of qubit that you can choose. You have to pick one to build your device. And both Google and D-Wave are using superconducting qubits. And Google has 72, and D-Wave has 2,000. So why doesn't Google just fall down and die? And so they're not the same kinds of qubits, even though they're both superconducting. So there's a lot of nuance that goes into discussing this. And there's also more to this statement of where we are than simply counting quantum bits. There's another aspect of quantum circuits called the depth, which has to do with the time steps associated with an algorithm. So this is a necessarily incomplete picture, but with all of its flaws, it gives us a rough understanding of where we are. We are already capable of doing QKD. We are on the boundary of being able to do meaningfully important quantum sensing, and hopefully soon we'll be able to do one of the sort of 2 big categories of quantum computing work, which is the bubble on the upper left, this NISC era that John Preskill has identified. That's what's encompassed in the bullet in the bubble in the upper left. The problems that are in that area may not be as romantic and dramatic as breaking the codes of somebody who you want to understand, but there are very, very important problems in this area that include, amongst other things, the potential to develop new kinds of medicines and to understand molecular structure in a way that we cannot now. I have to be clear about what I'm saying. We understand the quantum mechanical equations that describe molecular structure for anything you might want to think about. What I mean by that is that we know what the equations are, we know precisely what the equations are that you need to write down in order to characterize anything. But we can't solve the equations except for the very simplest systems analytically, and even using classical computers, you get to a point quickly when you get to a sufficiently complicated such system where you can't solve it in any efficient way using a classical machine. And that's something we'll be able to overcome in the NISQ era. I want to talk about reality here for a second. So I have been depressed to discover recently that as I ask people in audiences, who remembers Felix the cat, that number keeps on dropping. I will disagree with Arthur C. Clarke. And even whistle the theme. Excellent. So this is why it's always good to have Jonathan in an audience whenever you speak. And so Felix had this magic bag of tricks, and with this magic bag he could solve any problem. If there was a mountain in front of him, he took out of the bag a hole, and he put it on the side of the mountain and walked through, and he put it back in his bag. This is not what we have in quantum information science. I disagree with Arthur C. Clarke's characterization of any sufficiently complicated technology being indistinguishable from magic. It's not. You just have to take a class in physics, and then you see it's not magic. And so this is hard-nosed, calculable physics. Physics is different from philosophy, or God help us, politics. You sit down with a piece of paper and a pencil, and you calculate. And it doesn't matter whether you're in Alaska or Madagascar. If you get the same answer, you've done physics. And maybe somebody here knows what Tannstoffel is from Heinlein. So there you go. So there ain't no such thing as a free lunch, and that's certainly true in physics in particular, and in quantum mechanics especially. It's science. We know what is what. There are boundaries. You can't just wave your arm and make something bump, even though entanglement at first looks like that. So I'm going to tell you a little bit about what entanglement cannot do, but rather than be vague, I want to show you how we actually generate entanglement. I say we, I'm a theorist, so I don't do this. But the experiment, this is one way of doing it, and it is the way that is being done right now in our laboratory at Princeton, and you name it, wherever people generate entangled photons. They use this method. It has a name. It's called spontaneous parametric down conversion. Of course, there's several versions of it. I'm not going to go into any of the details, but you have a laser, and the laser irradiates another laser. The first one is like a flashlight. It's a continuous wave laser. The next one is like a machine gun. Bullets of light come out of it. That's the second laser there. And a number of optical components are irradiated. The light is allowed to pass through specially cut and coated and shaped crystals that do things to the light as the light goes in. And the most important of which is this crystal here. This one is interesting. If it's cut the right way, a beam of energy, a beam of light with a certain amount of energy comes in to the back, and two beams come out at a certain angle with half of the energy of the incoming beam. Then what's done is that we polarize the outgoing light. I want to remind you what polarization is. So when the electromagnetic field, when you turn on light, like it's coming from the sun or the light bulbs, the electromagnetic field is coming out of the source. There's all kinds of vectors that you learn about in electrodynamics. There's one called the electric vector, which is not the same as the electric field vector, or not the same as, it's called the electric, and it points in the direction that the thing is moving, and it traces out as a picture. It's like an artist, as the field is moving forward. And if it's not coherent light, if it's just any old light, it traces out a squiggle, gibberish, as it moves forward. If the light has been polarized, which means that it's been passed through a material that does this interesting phenomenon called polarizing, then it doesn't do that gibberish anymore. The electric vector tip traces out a picture. Generically, it's an ellipse. And if you switch the ellipse this way, it turns into a line, and that vector goes back and forth along a line. That's a linearly polarized field. If you squish it the other way, it becomes a circle, and that's circularly polarized light. Or generically, it's an ellipse. So let's talk about vertically polarized. So I can do that. I can have it just like the polarizing filters that you probably played with as I did as a kid. You turned them and the light went black. And so you can organize this line so that it's horizontal, call some direction horizontal, and then the direction perpendicular to that is vertical. We have that polarization applied to the output of the crystal, and what is produced is a cone of light. So this picture here is actually not the rest of this is a cartoon, but this picture is actual data taken, in this case from our lab. The colors are artificial, but where the two cone bases overlap, the photons there are entangled. And the symbol there, what it means to be entangled is that the two parts are not two parts anymore. There are two parts, but they're not parts of two different things. They're two parts of the same thing. And it's not possible to talk about this complex of two photons without talking about both of them together. It's probably not, look, to do this correctly, you need to write down in detail exactly what I'm talking about, but these are impossible to describe separately. So there's a horizontal part that is tied to the vertical part, and there's a vertical part that is tied to the horizontal part. The interesting thing is that, although it's not really two things anymore, it started out as two, so we think of it as two. And you've all heard about the experiment where you put one of these two pieces in my office at Princeton, and then you get the other one to Pittsburgh. And so that's a trick to get that to Pittsburgh and keep it entangled. But let's overlook the engineering challenge and imagine that somehow it stays entangled. And there are 4 ways to entangle two spin 1/2 particles. One of the ways is such that if I measure one of these two pointing up, the other one, say, could point down. So the obvious question that people think at first, intelligent people think, but they're mistaken, is that Paul Revere could have done one if, up if by land, down if by sea. You can't do that. You can't communicate classical information. And I want to give you a quick thought experiment. The proper description of why you can't do that takes a little bit of mathematical precision. But I can say words that are in this case actually correct. I say it that way because usually if I, as a physicist, tell you something, it's always incorrect, partly, because I have to leave out the part I'm leaving out. But in this case, I can tell you everything in a verbal description of the experiment. So John Dowling is in Baton Rouge, and he's got one of these two, and I'm in Princeton, and I've got the other of the two, and we agree to do an experiment. But we do this as a scientific process, so we do a lot of repetitions to get good statistics. So I keep on measuring my spins, and I get up, down, whatever I get, and I keep a record. We agree on a time in advance, and so our clocks are perfectly synchronized, and John looks at his end, and he keeps his record. And then I play a trick on John. I don't tell him, but I go home, and I stop doing this. He doesn't know that because I didn't tell him. So he keeps on making his record.
You're a mean guy.
But I'm not really mean. The reason I'm not mean is because if I do this, your result is going to look exactly the same either way. The record that you would get if I had actually stuck to my guns and kept on making measurements would have been perfect white noise. You would have gotten up, down, and a random distribution, and I would have gotten the same. If I, in fact, left the lab and wasn't doing anything, you would be only able to generate the same thing at your end, and it would be impossible for us to distinguish these two experimental records. In other words, I could have dropped dead, and it wouldn't have been any different than if you can't, not only in other words, can you not convey information, you can't convey that anything happened at all using entanglement. So you might ask, well, if that's so true, you can't do anything, then can you do anything? And the answer is, yeah, you can do lots of things, but you have to do more clever things than saying it's time to buy the stock or time to shoot the gun. It's not simple to use entanglement. You have to come up with a non-trivial protocol. But the simple things that you might think you can do, you can't. And I want to say one other thing that you cannot do faster than light communication. It is true that whatever it is that happens, if I make my measurement in Princeton, that the correlated effect that John observes in Baton Rouge does happen instantaneously. What I mean by that is that the mathematical formalism that describes it doesn't have a slot for this, for time. Usually there is a slot for time. In this case, there isn't. There's no way to even, it's not incorporated in it. Or the better way to say it, you can take the time part and throw it away. It's not in the expression. It happens without the passage of any time at all. So doesn't that violate special relativity, which tells us that you can't go faster than light? And the answer is that it doesn't. The reason it doesn't is because although Einstein didn't formulate it this way when he first wrote down in German the description of all of this, but he would have written it this way if he had been thinking about information theory. But you can, the special theory of relativity does, in fact, prevent the propagation faster than the speed of light of an information-carrying signal. But in this case, there's no information, so there's no reason that it can't go faster. It doesn't violate any of the laws of special relativity. Very, very briefly, because I'm not focused here in this talk on quantum computing. Roughly speaking, there are three, there's a fourth one I haven't included here, flavors of quantum computing. You can formally show mathematically that these are the same as each other. The D-wave machine, which has been much talked about in the press, is a type of a restricted version of the second type. The second type that I've put there is called adiabatic quantum computing. The D-wave machine is actually not adiabatic quantum computing, but it's a somewhat restricted version of that that's called quantum annealing. And in contrast, what Google is developing is intended to be a full-fledged adiabatic quantum computer. I want to talk about quantum sensing, and I mentioned that it gives you the best possible image resolution. So Lord Rayleigh worked out in the 19th century the formula that tells us the relationship between the resolution that we can get in an image and important physical parameters, light, wavelength, and the size of the aperture through which the light is going towards the thing that it is illuminating. And it's roughly lambda divided by d. If you do the calculation right, which you do in a class on this topic, it's, for good luck, there's a number that's about equal to 1, but not exactly equal to 1 that you have to calculate. But it's approximately lambda divided by d. And that's why you have big telescopes, because of the factor of d in the denominator, because you want this ratio to be as small as possible. This ratio tells you in units of wavelength how close to each other can two objects be and discerned still as distinct from each other. So you want that fraction to be as small as possible, so for a fixed wavelength you want to make the diameter d of the telescope as big as possible. In quantum imaging, that gets modified. Lord Rayleigh didn't know this because quantum mechanics hadn't been discovered when he calculated this, but he would have gotten this result had he done it. There's an additional factor of n, where n is the number of photons per pulse that irradiate the target that you're looking at. So let's talk about that. The classical result is lambda divided by d. If you take into account the fact that quantum mechanics is the right description of things, and therefore you don't simply model what's happening as light illuminating a target, light waves, but quantum mechanical description of light, which means that it's both waves and a particle called a photon, then there's a number of those photons, and the number n per pulse appears in the denominator here, but how do I go back? Well, it doesn't matter. This is it's on this slide too. So then it turns out that the square root of that number is what appears if you do the calculation from scratch. You get exactly what Rayleigh got, including the number that I told you that's for good luck in the front, which is why I don't have an equal sign there. It's, if you then take these photons, which you've now counted, and you entangle them, you get an additional factor of 1 more square root of n, which gives you the final result of a full factor of n. So that means that if you have 10 photons per pulse that illuminate your target, you will see things 10 times closer together than you would otherwise be able to see. This technique uses a state, a type of way of entangling the photons that is called a noon state. And you're going to think he's paid me off, but he hasn't. Dr. Dowling has, in fact, done the seminal work on this 20 years ago almost now, on identifying the significance of noon states. It's a particular type of entanglement. And so using noon states, you can achieve this highest possible image resolution. And this is not just theory. It's already been demonstrated in many experiments. I've only illustrated it here with one. There was an experiment a few years ago done in Japan. Of course, they used the letter Q. They engraved it and they imaged it. And up to some experimental errors, the improved resolution that they demonstrated was exactly what the theory says it should be. These quantum effects are very, very real, but we don't somehow think that they're intuitive. I want to take a moment to talk about that with you. Why is that? So there is a famous American rabbi who's over 90 years old now. His name is Abraham Twersky, and he wrote this very deep but simple-sounding thing. If you walk down a slippery set of steps and you fall on your behind, you know it's going to hurt theoretically before you do it. But there's nothing like actually doing it to feel what it's really like. And so we can talk theoretically about quantum mechanics, but why don't we really feel it the same way we feel it if we fall on our behinds as we slip down a step? And so there are all kinds of physical parameters that are useful in describing the world around us. non-physicists and physicists alike know some of the most famous ones, the mass, the speed, the angular momentum, and so on. There's a lesser known physical parameter, perhaps to non-physicists, that is called the action of a physical system. For reasons I can't go into, it has a special role in this question of determining whether a phenomenon is somehow quantum mechanical or if it's acceptable to describe it using the approximation to quantum mechanics that we call classical mechanics. And it turns out that the important quantity, I hate saying it turns out, there's no time to explain in detail why, but it turns out that the quantity that determines this is the ratio of the action of the system in question to a specific standard amount of that action called Planck's constant. And Planck's constant is, so what is action? Action is, roughly speaking, it has units of energy multiplied by time, and roughly speaking it says how much energy is expended by a system during a given amount of time. It's a complicated integral over a certain quantity, and that's approximately what it is. And if you move around, open the refrigerator, get out a sandwich, one way of measuring energy and time is joules times seconds. So if you open up your refrigerator door and get out a sandwich or walk or turn on your car, or do ordinary things, you will be expending of order 10 to the third joule seconds of action. It's not exactly that, depends on how much you're doing, but that's a sort of a good figure of merit for how much action characterizes macroscopic activity. Planck's constant that I mentioned a moment ago in units of joules times seconds is 10 to the minus 34 of them. So the ratio of your human macroscopic action, 10 to the 3, to 10 to the minus 34 is 10 to the positive 37. In other words, a trillion, trillion, trillion times 10. The formula that you have to stick this number into is a number of order 1 multiplied by e, the base of the natural logs, the exponential function, raised to the power minus that ratio. So that ratio is, like I just told you, it's 10 to the 37. So e to the minus 10 to the 37 is 1 divided by e to the 10 to the 37, which is 1 divided by almost infinity, which is almost 0. And that number is a measure of how quantum mechanical the phenomenon that you're talking about is. So if you're doing an amount of action that we do in everyday life, the quantum mechanical effect that you are likely to see is approximately 0. That's why we don't float through walls, we don't tunnel through walls. But if you're an electron, that same ratio is it's in fact not the huge number that I mentioned, it's about 1, because the action of an electron is close to Planck's constant. So then everything is quantum mechanical. But because we are the size we are, and the things we touch are the size they are, evolution presumably evolved us to do well with the things in which we are embedded. So it would do us no good to be sensitive to things that never happen to us because of the size and scale that we are. So we don't have any intuitive sense of quantum mechanical things, other than what we can develop through the study of physics and a lot of exposure to the calculation. So I've been doing this every day of my professional life since I got my doctorate. So I have fooled myself into believing that I somehow understand this better than non-physicists. In some sense I do, but nobody really understands these phenomena. Nobody can, because we don't experience them. And we can only do that through instruments that we build. There is a problem with quantum sensing, which is that we have to propagate these entangled photons through a realistic atmosphere. There's a paper I wrote about, co-authored with several other authors about 12 years ago now, in which we calculated for the first time exactly what happens when you propagate these entangled noon states through a lossy atmosphere. And there are challenges that have to be overcome as a result of the physical phenomena that occur, and a lot of work has been done on this to try to get around that. Discussion took place earlier today about quantum cryptography. I want to talk about its unconditional secrecy. It is unconditionally secret if you do it correctly, except for the part that isn't. And Professor Ullman correctly fingered what it is that isn't, which is that first step, the zeroth order step, which is the need to authenticate. So I'm not going to advocate a stance on whether one should or shouldn't do QKD, but one argument that people will make is that you have to do authentication always, no matter what kind of cryptographic technique that you use. Since you have to do that, and that is not, there is no currently known unconditionally secret method of doing that. Since you have to do that, you have to do that. And if you then build on top of that the rest of the QKD protocol, that remainder is unconditionally secret if done correctly. So at least you've gained that kind of an advantage. This slide points mainly to the limitation of the need to authenticate, and the fact that wasn't stressed so much before, which is that QKD, in all of its current variations, there are about 20 different protocols that have thus far been discovered, is an intrinsically point-to-point protocol. So it's not cleanly and trivially internetizable, where we can send a message to as many people as we want at the same time, all governed by the same security guarantee. That's not possible. You have to separately do QKD with each recipient. I'm just going to show one more QKD slide real quick. This shows the protocol in detail. I want to show you how we might do a network. So here is a mountain range, which is not geographically accurate. I didn't realize that my animation had a sound attached to it. I hesitate to press the button that began because there's another vehicle coming in. This is Microsoft's fault, not mine. And so those are Alice and Bob, and they're not connected by a line of sight optical path, and let's assume they don't want to have an optical fiber stretched out between them. So if they can each see separately at a satellite, they can do QKD as follows. Alice can initially set up a key, K sub A, with the satellite. Bob can do the same with a different key, K sub B. And then if the satellite is a so-called trusted node, which is already in violation of the spirit of QKD because you're not supposed to rely on trust, but on the principles of physics, if you do trust the satellite and somehow know that there's no hacker on it or breaking into it, then the satellite that now has the two keys can compute the binary sum, the XOR of the two keys. And that binary sum is, so these are keys, so they're random sequences of bits, so they're information-less. But you want to keep the key that's of importance to you away from the enemy. But this other key, XOR sub AB, is information-less, like any random string. And I can send it to Bob from the satellite. It doesn't give the enemy any information. There's no information in it. And it's not the particular informationless string, K sub A, that I really care about. So that's fine, I can do that. And then Bob, who of course is in possession of key KB, can XOR his key against this XOR. And it's a property of binary arithmetic that we all know, that if I do this double XOR, I get out the first term, which is key sub A. So now Bob finally has key sub A, which he now shares with Alice, and now they can do, use this key as a one-time pad. And there can be, I'm not going to use this slide ever again. So they can, this can be a network of n Bobs, as many Bobs as you like. This is not a proper quantum network where the end-to-end features are what they are because of the properties of the physics of quantum mechanics. This is a stand-in, and this is what the Chinese did, publicly announced this a year ago when they did a video call between Beijing and Vienna. They did this kind of a setup. What we really need to conclude in order to have viable quantum communications and quantum sensing are quantum repeaters. Now, the word quantum repeater, the phrase is a misnomer. A classical repeater takes a weak, so I have a signal that I want to send from Ohio to Auckland, New Zealand, and as it moves on its way from Ohio, it gets weakened and weakened and weakened, and then I rectify it and I amplify it with classical repeaters and then send it on and it gets to New Zealand just fine. You can't do that with quantum mechanical states because of the no cloning theorem that was referred to several times already. And okay, that's good, but it's also true that the phrase quantum repeater is a misnomer. Nothing is actually repeated. What is actually done in quantum repeating is that entanglement, the distance over which entanglement is shared between separated nodes, is increased and increased and increased through a variety of different techniques that together are called quantum repeating. At the end of this process, you now have entanglement shared between Auckland, New Zealand, and wherever you started, New York, and then you can use that as a resource to compute or do quantum communications or quantum sensing. So that's what quantum repeating really is. It has the net effect of what would have happened if I had been able to repeat the quantum information, but I can't. So this is what we mean when we say quantum repeaters. This is the required missing technological piece that is standing in our way of having large-scale, internationally distributed quantum networks. And I expect that this will be, and we already have some quantum repeaters that have been built in the laboratory, but we don't have any scalable, robust devices that can be put into work in an actual communications network outside of a laboratory. I expect that will come very soon. So I think I'm done. Thank you very much.
Thanks very much. Thanks very